Let's start off looking at some substitutions. Substitutions for the ideal gas law. So there's some other things that we can solve for using the ideal gas law. Let's just look at a couple of relationships. If we have moles, and N is for the moles, and we multiply that times grams over moles, we can set that equal to grams. And again, that's just the idea of if I swung this underneath, they'd be equal to each other, just kind of manipulating things around a little bit. Continuing this thought process, we can say moles times molar mass, grams per mole, molar mass, is still equal to grams. Or one more time, we can say that moles is equal to grams over molar mass. And we can fool around this one more time and say molar mass is equal to grams over moles. So we have that understanding. And if we want to just look at just something else that's out there that you're familiar with, density, you could also do lowercase c. I think it's typically lowercase d. Let me write that. Density is equal to mass over volume. So m is going to be mass, and v is volume. Okay, so if we know our Pivnert equation, we now have an ability to kind of move some things in and out here and substitute. So we're going to focus on the N first for moles. So we'll say PV is equal to grams over molarity, and I'm getting that from here for N. And then everything else I was kind of leave as is, but then I'm going to move things around and solve for molarity. So I'm going to switch this with these guys. So molarity, or I'm sorry, molar mass. Molar mass is equal to grams RT over PV. And what this does for me is, given a variety of pieces of information, if I had grams and temperature and pressure and volume, I could tell you what the molar mass is of that substance, the grams per mole. Just something else you can do. Now, with the understanding that I have mass over volume, we could also make another substitution. If I knew the molar mass of something, I could bring in density for mass and volume, still have the RT, and then pressure down here. And if I specifically wanted to solve for density, move things around a little more, and there you have it. So I've got a couple new equations that I could use to solve for other aspects. Easy enough. Okay, let's do a couple more examples in our homework. Looks like we're on 33. Suppose, bring this over here so we can all see. Suppose you are given two 1-liter flasks and told that one contains a gas of molar mass 30 and the other a gas of molar mass 60, both at the same temperature. The pressure in flask A is X atms, and the mass of the flask is 1.2 grams. The pressure in flask B is half as much, and the mass of the flask, the other one, is also 1.2, so we have that commonality. Which flask contains the gas of molar mass 30 and which one contains the gas of molar mass 60? Okay, so let's kind of just organize some information here, and we'll say the pressure of one, and I'm just kind of working ahead here a little bit, RT and V, that's for gas 1. And then based on how everything else is all the same in here, there's a couple things I can cancel out. I can cancel out R, and I'm just making the comparison for other gases, and the temperature. So really what I'm looking at here, I can say, and volume was the same too, it was the same size container. I can say that the pressure of one gas in relation to its number of moles, basing all the information that I have within here. And for the other gas, same deal. As far as canceling things out that I know, 1 liters and same temperature and everything else, I can say the pressure of that one is also related to its number of moles. And going back with other information that I know this is true in regards to their molar mass. So therefore, I can make a substitution into each one of these equations. And in doing so, I have the pressure and its molar mass is equal to its grams, and then is equal to the pressure and its molar mass of the other gas. And notice this grams here, they both have the same mass. Therefore, they're equal to each other. So I can grab information out of both of these and say, okay, 1 atm, I'm just using that as a reference. I could put any pressure in there I wanted to. And molar mass of that gas. And the other one was half its pressure. That is stated. What would be its molar mass? So in order for this to be true, based on this other information, and given which is which, the one that is 1 atm, or just whatever value we wanted to put in there for it, that would be 30, and the other one being half the pressure, its molar mass must be 60. So what this is, it's kind of like a problem-solving type problem that forces you to kind of think about how you would actually approach it. And that's all it comes down to. So there's not something specific in regards to Boyle's law, Charles' law. This is strictly just kind of messing around with math. All right, let's do 45 as well. This is one of my favorite problems of the whole year. It's just kind of this weird, fun little problem. In an experiment reported in the scientific literature, a male cockroach is made to run on different speeds or at different speeds on a miniature treadmill while the oxygen consumption is measured. I have no idea. In 1 hour, the average cockroach running at that speed consumes 0.8 milliliters of oxygen at 1 atm pressure and 24 degrees Celsius per gram of insect mass. Wow, that's a lot of information. How many moles of oxygen would be consumed in 1 hour by a 5.2 gram cockroach moving at this speed? Okay, we are solving for moles. So starting off here, I will say N is equal to PV over RT, and then see if I can just plug in stuff that the problem gives me here. They tell me it is 1 atm. I know that the volume is 0.0, where is it at? 0.8 milliliters. I need to change it to liters because that is what it needs to be in here because of the R value is in liters. It has to match. So I need to slide decimal over 3 spots to have that be satisfied. So 1, 2, 3, 8 liters. The pressure, it tells me, actually, I'm sorry, I'm going to do the R value, 0.0821. I'm not going to write those units down. And the temperature, it told me is 24, but it has to be in kelvins. So add 273 to that, and 273 Kelvin. And that's going to give me an answer of 3.28 times 10 to negative 5 moles of oxygen. And remember, it was per gram of insect mass, and I think it tells me the mass of this little guy in here is 5.2. So it's 5.2 grams per, that much oxygen per gram of insect mass. So if I multiply that whole thing out, I get 1.71 times 10 to negative 4 moles of oxygen gas consumed total by our little critter. So that's how much oxygen this guy uses in respiration when he's going on this little treadmill. Okay, that's a pretty good place to break, and we will do part 2, the exciting conclusions to that problem, in the next lecture.